Welcome to our deep dive into advanced paradigms in stringology and network flow optimization. Today, we move beyond simple search loops. We will explore how algorithms like Knuth-Morris-Pratt and Boyer-Moore achieve linear efficiency by preserving information, and how modern complex sequence problems are being solved using network flow models. The discipline of stringology is a foundational pillar of computer science. While searching for a word in a document seems trivial, the problem changes drastically at scale. Whether we are analyzing genomic sequences or detecting network intrusions, we face petabytes of data. In this landscape, efficiency isn't just a luxury, it is an absolute necessity. Let's look at the cost of naivety. The naive algorithm aligns the pattern with the text and checks character by character. If a mismatch occurs, it shifts by 1 and starts over. In a worst-case scenario, such as a repeating pattern in a repeating text, the complexity explodes to big O of n times m. For large inputs, this creates a computational bottleneck. The fundamental flaw of the naive approach is what we call amnesia. When a mismatch occurs after matching several characters, the naive algorithm discards that hard-earned information. It forgets what it just saw and restarts from scratch. Advanced algorithms operate on the principle of information preservation, using previous comparisons to skip ahead intelligently. Before we dissect the algorithms, we must establish the rigorous combinatorial frameworks that govern them. We need to define the language of strings. Here are the critical definitions. A prefix starts at the beginning, and a suffix ends at the end. The most important concept for today is the border. A border is a substring that is both a proper prefix and a proper suffix of the same string. For example, in the string a-ba-ba, a is a border, and aba is also a border. Many advanced algorithms rely on the Z algorithm for preprocessing. This constructs a Z array, where each value represents the length of the longest common prefix between the original string and a suffix starting at that position. It efficiently utilizes a Z box to avoid rescanning characters, mirroring the logic we see in palindrome detection. Now we arrive at the inductive paradigm, the Knuth-Morris-Pratt algorithm, or KMP. Published in 1977, this was the first algorithm to guarantee linear time complexity in the worst case. To understand KMP, imagine the pattern as a state machine. When a character matches, we move forward. When it mismatches, instead of restarting, we follow a failure link. This link points us to the longest prefix that effectively matches the suffix of what we have just read. This ensures the text pointer never moves backward. The operational heart of KMP is the LPS array, or the pi table. LPS stands for longest prefix suffix. For every position in the pattern, this table tells us the length of the longest proper prefix that is also a suffix up to that point. If we mismatch, this table tells us exactly how far we can shift the pattern to align the prefix with the matched text. The beauty of KMP is its efficiency. The total time complexity is big O of n plus m. This accounts for the linear scan of the text, n, and the pre-processing of the pattern, m. Unlike other algorithms, KMP's performance is independent of alphabet size, making it perfect for small alphabets like binary or DNA. While KMP scans forward, the Boyer-Moore algorithm revolutionized string matching with a heuristic paradigm. It processes the pattern from right to left, allowing it to skip massive sections of text. Boyer-Moore combines two powerful rules. First, it aligns the pattern but checks characters from right to left. If it finds a mismatch, it calculates a shift distance using two heuristics, the bad character rule and the good suffix rule. It then applies the maximum of these two shifts. The bad character rule is simple but aggressive. If the character in the text doesn't match the pattern, we ask, does this character exist elsewhere in our pattern? If yes, we shift to align it. If no, we know that no alignment covering this position can work, so we skip the pattern entirely past this point. The good suffix rule handles cases where the bad character rule is weak. If we matched a suffix of the pattern before failing, we want to align that matched suffix with another occurrence of itself earlier in the pattern. This is mathematically more complex, but essential for small alphabets where bad characters appear frequently. In the best case, Boyer-Moore runs in sublinear time, skipping through the text. However, in pathological cases, it can degrade to quadratic time. To prevent this, we apply Galil's rule. This heuristic memorizes the end of the previous match to avoid recomparing known segments, guaranteeing a worst-case performance of big O of n plus m. In practice, engineers often use simplified variants. The Horspool algorithm drops the complex good suffix rule, relying only on the bad character shift. Sunday's algorithm looks at the character immediately following the current window for even larger jumps. For general text, these are often faster due to better processor cache locality. We now move to the cutting edge. Complex string problems, like reconstructing a genome from fragments, are increasingly solved by reducing them to network flow optimization problems. In bioinformatics, we reconstruct genomes using de Bruijn graphs. We can treat the graph as a flow network, where the flow on an edge represents the abundance of that DNA sequence. This allows us to construct Flowtigs, safe paths that traverse through ambiguous branching points by following the flow values, significantly improving assembly quality. Beyond assembly, we apply flow to complex matching, specifically pattern matching with variable length gaps, where the distance between characters varies, can be reduced to a maximum flow problem on a layered graph. Additionally, approximate matching, like aligning similar names, is modeled as a bipartite matching problem, solvable via min-cost max flow. We have traced a clear evolution. We moved from the redundant verification of the naive approach to the inductive reasoning of KMP and the statistical heuristics of Boyer-Moore. Now we see the future in network flow, where discrete string combinatorics merge with continuous optimization to solve the most complex data challenges.